Okay, so another fundamental idea, a very ancient thing, again. It's, so in my last lecture I talked about the sine rule, and I gave a rather spectacular, what I thought was spectacular example and of the use of it. And I would like today talk about the cosine rule, which is once again another relation which should be familiar to you, well, more or less, perhaps modulo a few harmless misunderstandings from very early days in your studies. The cosine rule, it is in fact, it's a slight generalization of the famous theorem of Pythagoras. So, of course, the theorem of Pythagoras is about right triangles. So let's take an arbitrary triangle, not a right triangle. So, and let me consider the situation where first A is an acute angle. Okay, so that if I drop a perpendicular from B onto the side CA, then let's call the foot of the perpendicular K, if you like. Okay, so this is the angle A. Let's call it. This is the side A. This is the side C of length. The length of line segments BC is small a, and the length of AB is C, so that the length of the line segment AK will of course be C times cosine A. So that would mean that the line segment, the length of the line segment KC, this is right angle, is going to be B minus C cosine A. So that results in, so use the theorem of Pythagoras on the right triangle KBC. So theorem of Pythagoras. And KBC. That gives us, of course, there's one thing which I forgot to mention. Of course, the length of this altitude is, in this case, C times sine A. Well, putting them all together, this is C times sine A, this is B minus cosine A, this is A. Well, this gives us A squared equals A squared, the square of the hypotenuse, is equal to the sum of the squares of the sides, right sides, C sine A squared plus B minus C cosine A squared. Well, if you manipulate it just a little bit, this will get you, of course, C squared sine squared A plus B squared plus C squared cosine squared A minus twice BC cosine A. Well, the rest is quite obvious. Sine squared A, cosine squared A add up to give you 1. So you end up with the following equation, that A squared is in fact quite simply B squared plus C squared, which would have been the theorem of Pythagoras in a triangle where the angle A is right angle, but in general, you've got this correcting term. Well, that equation with the correcting term is called the cosine rule in the triangle, in a triangle. Okay, of course, I leave it to your imagination. I leave it to you to formulate. Of course, while I formulate this rule, I have, of course, assigned the vertex A a spatial position, a privileged position. So you can do it with the vertex B, vertex C, and you obtain, I think, the all too familiar formulae. There is one thing perhaps you should think about. What happens, so that's the case where A is acute angle. So what happens if A is an obtuse angle? Well, if it's an obtuse angle, then you have got something like this, something like this. If A is obtuse, you will have something of this shape, okay? So that you have got a more flat triangle. That's the side B. That's the vertex B, that's the vertex C, that's the vertex A. And if you drop a perpendicular from B onto the side CA, then your K will live in this part of the world, whereas A will be in this part of the world. So that's a right angle. So you can do exactly the same thing. This side is A. The length of this vertex is, of course, yeah, this is C, this is B, okay? So the length of this altitude is, of course, yeah, C times, this is A, and its complementary has exactly the same sign. So this is C times sine A, whereas, of course, this is C times cosine A, C times cosine A. Yet, C times cosine A, yet you must have, of course, a minus sign in front of the thing, because this is the complement, this angle complements A. So these two, the angle A and the angle in question add up to give you pi, so this minus. So if you add these things together, you will obtain once again B minus C cosine A, and of course the rest of the story goes just like in the first case. That's the cosine rule. Quite as simple as that. So this must be something familiar to you all. All I have done is just to give you a tidy exposition once again. Well, let me give you some applications. Şimdi, okay, so I don't know, it's all up to, it's all a matter of experience, but according to my experience, which is pretty considerable looking at my age, cosine rule seems to be the more versatile one. Okay, so it's more frequently employed to obtain rather spectacular results in elementary geometry. So I shall give you 4 or 5 results, and they are all rather interesting. Well, the first one is I call it application 1. I'm not going to do the computation. It's good, it's interesting, but it does not concern me primarily now. But let me tell you that in the Morley configuration, in the Morley theorem, Morley trisector theorem, trisector theorem, you have got this equilateral triangle, remember? Do you remember? You had this equilateral triangle, K, L, M, and you had all these. Okay, so for instance, you had this C, and this was gamma, and gamma, and gamma, and you had also, okay, so that you had this, and you will remember I was careful to paint it red. I find it so interesting and so important. So this Morley triangle, you can actually compute the side of this equilateral triangle. You will remember in my lecture, in last lecture, I computed actually these lengths, CK, CL, etc. So you can actually move forward, and you can actually compute KL by using the cosine rule. So in fact, it turns out that KL length, and of course it's exactly the same as the length of LM, and of course it's the same as MK. All these lengths turn out to have a very beautiful value, and it is, if I am not far too wrong, if I remember correctly, yes, they are in fact 8R, which is rather beautiful in my opinion. Sine alpha, sine beta, sine gamma. You remember alpha, beta, gamma were respectively the thirds of the angles ABC. Okay, so this I think is a rather nice formula. Okay, so let's say I'm not going to deal with this. This is left to the student. Left to the student. Have a go at it, along with the problems I have assigned this week. Check that your problems, the second problem sheet is published. Okay, check it out and have great fun with it. It's full of really very nice examples. Okay, so that's the first application, which is rather nice, but as I say, I'm not going to do it. And the second thing is another well-known aspect, an historical object, in fact, so it's application 2. And it is well, once again, I've forgotten to bring along my historical notes. I shall compensate for it. I shall give you full details about the persons making their appearances in this talk. Heron's formula, the Heron formula. You know, like all things in mathematics, nobody knows whether actually it was Heron who actually established this formula, but it's widely used. So let's stick to it. Heron formula in a triangle, the area. Okay, so delta. Let me denote it by delta. Delta of that's the area of the triangle ABC is given by the very, very cute formula. S of course was, as you remember, the semi-perimeter, the half the sum of the three sides, A plus B plus C divided by 2. S, the semi-perimeter. S times S minus A times S minus B times S minus C. Well, that is not actually this area, but it's squared area. So if you take its square root, you will get the area. Okay, so it's rather, of course, I mean, the Heron formula historically was not proven. I mean, the earliest proof I know is not in any way by employing the cosine rule, but this can be proven very nicely using the cosine rule. Let me show you. Let me show you how it is done. Yeah, let's start with the fact that the area of the triangle squared. Okay, the area of the triangle is, of course, what? A half. Let's say, I don't know how you like to do it, but yeah, of course, what you can, yeah, okay, so you can take B and you can multiply it with the corresponding altitude, which is C times sine A, so it means B times C times sine A divided by 2. So the area is, in this case, B times C times sine A by 2. So let's take the square. Well, that will give you, of course, 4B squared C squared sine squared A. Well, the first thing that you do, the first thing that you do in this case is to replace sine squared A with cosine, with an expression involving cosine. Okay, so let me do it like this. B squared, C squared. It takes a bit of, it's a bit of manipulation, but it's really hardly anything more than elementary. So cosine A, you see another way of seeing this formula may be seen not only as a relation between three sides and one angle, but you can also see it as a formula which gives the cosine of one angle in terms of the sides. So for instance, from this I can write cosine A equals B squared plus C squared minus A squared divided by 2 times BC. Okay, so let me use this. So instead of cosine A, I substitute that value. So I obtained B squared C squared by 4 times, here we are, 1 minus B squared plus C squared minus A squared divided by 2BC. Now this object, this is rather big one, is squared. Okay, so that looks good enough. That looks good enough. I would like to manipulate this just a little bit, So for instance, let me, okay, so how do I manipulate this? There is 4 squared. So let me take 16 outside so that I can have a nicer, situation. And let me push B squared C squared inside the square brackets so as to obtain this. B squared, of course, 4 times B squared C squared minus this, well, rather intimidating quantity. Okay, so that seems to be interesting. Okay, now let me once again do the obvious decomposition, factorization of this thing. So that gets me, okay, so 1 over 16 is here, which will stay there for a rather long time. So this the difference of 2 squares, so I can write this as follows: 2BC minus, what do I have? B squared plus C squared minus A squared. Okay, and of course I shall multiply it with the same thing. 2BC plus B squared plus C squared minus A squared. Fine, that's great. Okay, as you can see, it's quite a bit of manipulation, and you know this sine rule and cosine rule are especially good if you are not intimidated by big formulae and just push forward and do your calculations, and you know, but you have to be careful. You have to watch out for the critical moment where a devilish clever manipulation will give you the result. Okay, so watch out always, but don't be afraid of brute computations. Okay, so how about this? So you see, this kind of thing can be a little bit simplified like this. So you've got, okay, so let me start with the first one. For instance, you've got A squared in this part of the world, yet you've got B squared C squared minus 2BC. So I can write this first one as A squared minus B minus. Observe the way I'm slowly but surely transforming this object into something interesting. Now let's look at here. You've got B squared plus C squared plus 2BC, which is obviously B plus C squared. And we have got, of course, minus A squared. Now, once again, let's use our critical knowledge of difference of 2 powers. So you've got 1 over 16. So I can write this as A minus B minus C and A plus B minus C, which is fantastic, it's great. And in this part of the world, I can write this as B plus C minus A. And well, we are done. We are actually done. We are finished. B plus C plus A. We are finished because you see, A plus C minus B. This object, in fact, gives me 2 times S minus B. Okay? And this object gives me twice S minus C. And this, rather obviously now, 2 times S minus A. And this, of course, is simply 2 times S. So you've got your 4 times 2 to the power 4, which will cancel out with 16, and there you are home free. Right. So that's how you do. Okay, yeah. So this tells us that delta squared is in fact, so you've got delta squared is in fact what? S times S minus A times S minus B times S minus C, and then taking the square root, you will, of course, get the historical Heron formula, which is a rather beautiful thing. You know, it is, it's no, I don't know, I really wish you could perceive the content of these results in their true historical perspective. It's, you know, it's a rare accomplishment to compute the area of a triangle in terms of its side lengths. It's not a trivial thing to do, especially in ancient times. Right. So, as I said, I mean, I don't know. Of course, it's all personal experience, but looking back upon my own experience, I have found that cosine rule is usually more flexible, more versatile than the sine rule. But you know, it all depends. There is one, how should I say, one corollary that you can derive from the cosine rule. It's especially important. It's especially important, and it has been associated with the name of Stewart, another historical person about whom I owe you some information. Okay, so now that's the third application which I would like to bring to your attention. Now this, as I say, will be a direct consequence of the cosine rule, but it's so useful. It's one of the most useful elementary results that you can learn about. Application 3. It is what has come to be called Stewart's relation. Naming things, naming theorems after the persons, you know, this business of eponymy. Okay, so calling something theorem of Pythagoras, theorem of Simpson, theorem of Heron's formula, so on and so forth. I think an American statistician called Stephen Stegler, I'm not quite sure how to pronounce his name, has observed that almost no mathematical relation, eponymous mathematical relation, is named correctly. And he gives, for instance, the example, well, it's well known. Simpson line was actually invented by Wallace. The Zhukovsky aerofoil was invented by Otto Blumenthal. Cartan matrix was invented by Killing. Killing form was in fact invented by Cartan, and you know, and in fact, rather humorously, he observes that this law, this Stegler's law, was invented by someone else called Merton much earlier. So you know, it's all these names. All these names they are not very accurate. Nobody knows really who first observed what we nowadays call Stewart's relation, okay, or Schall relation or whatever. Okay, so all the same, I think it's a good way of stopping and thinking about the history. Right. Okay, so Stewart's relation. It is the following. Okay, so allow me to proceed to derive the thing first, and then I shall state. So it's not like, I mean, not like conventional mathematics where I state the theorem and then give the proof. No, let me derive the thing, and then at the end I shall put it inside a box, so you will understand. Now that's Stewart's relation, right? The idea is the following: you take a triangle, and in this triangle, well, of course, I will formulate the situation in which I give the vertex A a rather privileged position which of course need not be. Instead of A, you can use any vertex. Anyhow, the sides BC is divided into two pieces, okay, by a point, let's say Z, and the pieces are P and Q, not in length. Okay, and the rest, of course, is usually, so P and Q, okay, so P and Q add up to give the side length A, which is the length of the line segment B, line segment BC, and of course the line segment CA has got length B, and the line segment AB has got length C. That's the usual stuff. Now, here is the thing. You are also given the length of the line segment AZ. Okay, and let it be X. So I'm putting it in sort of handwritten X to indicate that it is lowercase x. Right. So the following happens. You can apply the cosine rule in the triangle ZAB. So, and let's call this angle theta. Okay? So the cosine rule, I'm applying the cosine rule. The cosine rule I apply first in the triangle ZAB. Okay, so let's do things counterclockwise. ZAB, okay. ZAB. If you do that, what you get is the following. ZAB. The opposite side squared, C squared, is equal to, C squared is equal to X squared plus P squared. So let me write it like this. X squared plus P squared minus, of course, 2 times XP cosine theta. Are you with me? Okay? So this is the vertex Z, and you are writing the opposite side in terms of the rest of the sides. Okay, just like A squared equals B squared plus C squared. No, minus 2BC cosine blah blah. Okay, so let's do that. Good. Now apply the cosine rule, the same thing, in the triangle this time, not ZAB, but ZCA. Well, that will give a rather similar formula. Now, in this case, the side opposite Z is B, and it's B squared. Well, B squared is equal to X squared, which is fine, plus Q squared. Now, here comes the thing. Of course, the angle at the vertex of Z, of the triangle ZCA, is the angle that complements theta. That's to say, this is pi minus theta. So its cosine is exactly the same, except that it changes sign. So it is 2x decat, attention, 2xq cosine theta. Right. So I've got 2 formulae which are really screaming to be manipulated into something significant. And of course, the obvious idea is to get rid of the theta, angle theta, so as to obtain a relation purely among lengths, which would be something quite desirable. And how can you get rid of cosine theta? You've got P in this part of the world, Q in this part of the world. So the obvious thing to do is to multiply this equation with Q and this equation with P and add them together. So what happens? I multiply C squared with, okay, so I've got C squared Q and B squared P equals X squared Q, X squared P which is fine. And then P squared, of course, p squared q plus q squared p. Okay, so there we are. The part involving the angles is just dissolved into nothing, dematerialized. It's just disappeared. Okay, so what do we have here? So p plus q is, as you know, a. This piece can be written in the following form: pq, p plus q. So I can actually write it as a times pq, which is great. So I have got so I've got the following formula: a times x squared, a times x squared, and this is how I like to write it. I don't know. It's all a matter of taste. You can write it in any way you like. P squared, v squared, and then of course I've got this minus. Yeah, I think a. Okay, this is how I like to write it. You can write it in any way that you wish. This, ladies and gentlemen, is the Stewart relation, which is an excellent handle to problems where you wish to find relation between closely situated distances. That's an excellent thing. So that's Stewart's relation. And yeah, and I will. I mean, I find it's so useful. I use it so frequently that I will actually stop here and give you one or two applications of not the cosine rule, but the Stewart's relation itself. So I mean, Stewart relation, in fact, seems to be even more useful than the cosine rule itself. Which is fascinating, right? So let me go to the other side of the blackboard again, and where is my eraser? Okay, so well, you see, I think you may have heard about the following. Of course, I think the easiest application would be example of the uses. Okay, so let me give some examples as to how to use this thing. Example. Okay, so for instance, you can actually compute the length of the median, which is rather interesting, in my opinion, the length of medians. It gives you a nice formula. Okay, here we are. Okay, it's a very simple picture. Here is your triangle. Here is your triangle, ABC. I'm doing it with special reference to the vertex A. You can, of course, change it around. Here is the midpoint of the line segment BC, A prime, and of course this is the line segment, okay, which lies on the median. Median is the line that joins A and A prime. So let's forget about that, and let's look at the. Okay, so we are interested in computing the length of MA, median through A. Okay, so the rest is obvious. So this is B, this is C. This is your A over 2. This is your A over 2. So this is a very simple application of Stewart's relation. In that the lengths of the subline segments into which BC is divided, that's P and Q. P and Q are both P and Q are both A over 2. So let me just write it down. So the Stewart relation says that A times the square of this thing, isn't it? A times m. Well, let me write just m. Okay, so you can repeat it with am squared is equal to well, p is a over 2 times b squared plus q is again a over 2 c squared, and then of course minus a times P and Q, they're both A over 2, A over 2. So let's cancel A's. And you are left with M A squared equals a half B squared plus a half C squared minus a fourth A squared, which is, well, in my opinion, a rather fine formula. You can take the square root. There we are. That's it. So you have computed the length of the median. That's one of the easiest things that you can do by a straightforward application of Stewart's formula, Stewart's relation. I would like to give you one more application of Stewart's formula, and that will have rather interesting results, historically and geometrically. It is, yeah, let's try to do that. Let's try to do this with angle bisectors. Angle bisectors. Now, can we compute? May we compute the lengths of angle bisectors? Well, it can be done rather nicely. It can be done rather nicely. Okay, so yet another example, let's say. The length of internal angle bisectors. What I mean by these. Okay. By the way, I'm leaving it entirely to you, and I find it an important exercise, and I really expect this of you. That means I shall be seriously annoyed if you can't change the symbols around so that you can write the formulae for MB, MC in a similar fashion. Okay, so just cyclically pushing the things around to obtain the correct formula. That's very important for me. Okay, I mean, that's at least as far as the computational aspects of the triangle go. Right, okay, so let's do this, the length of the internal angle. Yeah, well, very much the same idea can be pushed, and so you apply the Stewart's relation. Okay, so, well, let me make the situation precise. So this is the vertex A, B, C. Now let me take the bisector, internal angle bisector through vertex A. So it intersects the opposite side in a point, well, which you have, I think, called J. Actually, I would prefer JA, but J will do for the moment. And yeah, we would like to compute its length. Let's say N, or N sub A, if you like. So as usual, this side it has length B, this side has length C, and of course our problem is to find P and Q. Okay, so how are you going to? So what is P and Q? Şimdi çocuklar, I don't want to stop for that. I would like to assume that I will do that. It's a well-known result that an internal bisector divides the opposite side in the ratio of the adjacent sides. That's to say this JA B divided by JAC is in fact minus JAB. JAC is equal to the ratio of this to this. Let me make this precise. Okay, so AB, AC. Well, if you wish, this is minus C to B. Now, why is this happening? Okay, I really did not want to do that, but let me make it very fast. I mean, it's a very simple idea, so perhaps you might as well remember it. So all you have to do is to remember that, okay, so the point JA is equidistant to the sides CA and CB. Okay, so this is, for instance, let's call this H. Okay, so the area of CAJ, the ratio of the area of CAJ and BAJ is of course H times B to H times C. So you can do it like this: area of J. Let me write J, not JA. JCA JAB. Well, this is in fact very simple. This object is b a half b times h. This is divided by a half c times h. Okay. Now this area can also be written as, okay, so, well, let me change my notation. Instead of h, I will take k. That's better. Because you see, I now want to use the real altitude of the triangle, which I shall denote. Now I shall denote this h. So you can, okay, so the same ratio is of course equal to the length of JB to JC. Well, I'm sorry. The area of JAB is of course JB times H, of course half in front of the whole thing. And the area of I'm sorry. I'm sorry. The area of JCA is simply the length JC times H, so JC times H, and the area of JAB is JB times H, of course with the half in front of it. Halves cancel out, H cancel out. I'm left with JC over JB in absolute value, so K's cancel out in this part of the world. And of course half. So the ratio of the length JC to JB is exactly B to C. So if you also take into account that J divides the line segment BC internally, the ratio of JB to JC is exactly minus C over B. Okay, that's beside the point. Not beside the point, but this I should have assumed as known. So I've just squeezed this piece of information in. Now let's find P and Q. Well, that's not too difficult. Since the internal bisector divides the opposite side in the ratio C to B, well, this P is simply C divided by B plus C times A. That's your P, obviously. And this Q is obviously the B part out of B plus C of A. So this is B plus C times A. So this is the, okay, so, and this is your Q. Fine. Now let's throw everything in and see what the Stewart relation tells us. And it will be very fast. It will happen very fast. It will happen very fast. So let me, yeah. And we shall end up with a rather beautiful formula. And I will apply that formula to another historical problem. Okay, there we are. Right. So, Stewart relation. So I would like to know the length of this thing. So A n squared. Let me omit the sub A is equal to, okay, P times P times B squared. So it is C, B plus C, B squared. And Q times, which is B plus C, C squared. Minus, of course, A times P times Q. So it is A times, Right, now let's see if we can make head or tail of this thing. Have I got something wrong? Yeah, I've forgotten A's, so I've got A. Let me cancel out these. Okay, so here I am. So n squared turns out to be now. Now I've got to be careful. I keep making stupid mistakes with these things. So n squared is, in fact, yeah. Okay. So you see, this is actually b squared c, bc squared. So I can write this whole thing as bc, b plus c, and b plus c. So if I put them on common denominator, I have to multiply with bc prime. So it is something like this, çocuklar. bc. I mean, it's not something like, it is exactly this. I'm just trying to make it as pleasing to eye as possible. Okay. Yeah, and C, of course, I should not forget. Divide by, yeah, there we are. We're almost finished. We're almost finished. A rather nice formula is almost there, Şimdi çocuklar, of course, you can write this nice formula in many different forms. I prefer to write it like this. I take out B, here, let me see, yeah. Okay, so I like to write it like this. B plus C squared, so let me take 1, so let me think of this as a separate identity. And then let me write b times c. And now what remains is the difference of two squares, b plus c minus a squared. Okay, so I've got b plus c plus a, b plus c minus a. Okay, so there we are. We are almost finished because you see, this object is twice the semiperimeter 2s, and this object is twice semiperimeter minus a. So I've got the rather nice formula. So let me take the square root of both sides. So I've obtained n a equals, I've got 2 on the right hand side, 2 divided by b plus c, and inside the square root sign I've got, well, s minus a. This rather goes like the area formula. So you would like the s minus b, s minus c. No. Instead of that, you will have b, c. Well, that's it, çocuklar. This is, in my opinion, a very beautiful formula, which allows you to actually compute the length of the internal angle bisector in terms of the 3 sides. Most remarkable. And I think, if I am not far too wrong, this is a good time to stop.